Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 103, Waves and Oscillations. Today it is the 24th lecture of this course and the topic is supersonic waves, shock waves. First, I will give the learning objectives. At the end of this lecture, the student will understand the sketch of the bunching of wavefronts for a sound source traveling at the speed of sound or faster. Also, they will be able to calculate the Mach number for a sound source exceeding the speed of sound. Also, they will be able to understand the relationship for sound waves exceeding the speed of sound. They will be able to apply the relationship between the Mach cone angle, the speed of sound, and the speed of the source. Here, I will recommend the student to first go through the lecture number 23rd, which is about the Doppler effect, in order to understand the supersonic speeds. Now, in this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. In this lecture, I have taken some of the figures from this book. Okay, as I told you that please go through the lecture number 23rd first before understanding the supersonic speed, or in another word, the shock waves. So we start with a question that is more or less related with the last lecture that was about the Doppler effect. Now, if a source is moving towards a stationary detector at a speed Vs equal to the speed of the sound waves. If you remember, we have discussed this equation of the Doppler effect. We know this is the general form in which one can relate this equation to any of the four cases that we have discussed in lecture number 23rd, where this V represent the speed of sound waves, this VO represent the speed at which the observer moves, this Vs represent the speed at which the source is moving. So now we start this lecture with this question, that if a source is moving towards a stationary detector at a speed Vs equal to the speed of sound, that is, the detector or the observer is at rest, so VO will be 0 here in order to understand the supersonic speed, and the speed of the source is equal to the speed of the sound. V and Vs are will be the same. Now, also we are saying that moving towards the stationary object, so in that regard, in lecture number 23rd, we have discussed that we will use this expression with V minus Vs. So if this Vs is equal to V and the detector of the observer is at rest, so then this equation will reduce to this form, that is, the observer is at rest and the source of sound is having a velocity V, and that is equal to the sound speed. So this equation further takes this form, that is, if Vs, which is the speed of the sound, source of the sound, if that is equal to V, so that the denominator will be 0 and the shift in the frequency will be large, that is, the observer will detect a very large frequency as compared to the frequency of the sound produced by the source. That is only when the source is moving with velocity of the sound. So we can say that the detected frequency f prime will be infinitely large. And if we see this through this figure, if you remember in the last lecture we have discussed, when the source is moving, the distance between two consecutive wavefronts will not be the same. So if we see here that source of sound is moving with the velocity vs, which is the velocity of the source. If that is equal to v, so if we see here and that is moving towards a stationary observer, that is v naught is equal to 0, we have an observer. So the observer will record a sound with a frequency very large. We see this in a very small portion. There are large number of wavefronts, or we can say there is no difference between the two successive wavefronts, because the speed of the source is equal to the speed of the sound waves. Now, as here an observer will see that the frequency of the sound will decrease, but on this side, as we have taken the condition that the stationary observer is there and the source of sound is moving towards that observer. So in that situation we see there is almost negligibly small difference between two successive wavefronts, so that there will be a large sound detected by the observer. So this means that the source is moving so fast that it keeps the pace with its own spherical wavefronts. As I told you in the last lecture, we have discussed when source is stationary, the wavefronts are spherically symmetric, and the difference between the two successive wavefronts is equal. But when the source is moving, we will be having a profile of the sound wavefronts like this. Now, but in order to go to the supersonic speed, now the question is that what happens when the source of the sound is having a velocity which is greater than the wave speed, that is the speed of sound. That is, if this Vs is greater than the speed of sound. So for such supersonic speed, that is the speed of the source is greater than the wave speed, or we can say the sound waves are now having smaller velocity than the speed of the source. So in that regard, the Doppler equations or the Doppler effect no longer apply. So what we do in such situation? So we start with this, that in order to understand the supersonic speed, we will just limit our discussion to this situation, that is when the source is moving with a velocity which is greater than the speed of sound. So in that situation, the supersonic speed, for the supersonic speed, the Doppler effect no longer apply, that is the equation will no longer be valid. So in such situation, now if we see this point representing the source of the sound that is moving with the velocity Vs, that is the speed of source. Now that the source is ahead of the waves, that is because the speed of wave is smaller than the source speed. That is, this figure depicts the spherical wavefront that originated at various positions of the source. That is, as it moves, so these wavefronts are produced by the sound source at different position. Since this is moving with the velocity Vs, so these different positions can be tracked with this formula S is equal to Vt, since the speed of the source is V and then T is the time that is between two successive wavefront that it emits. So the radius of any wavefront is Vt, where T is the time that has elapsed since the source emitted that wavefront. So if we consider this larger one having source at this position, and it traveled after a time t, a distance vs into t, and this is the radius of that sound wavefront equal to vt, where v is the velocity of the wave and this vs is the velocity of the source. Note that all the wavefront bunch along a v-shaped envelope in this two-dimensional drawing. We can see that as it moves, so that with the passage of time this wavefronts keep on bigger and bigger, because the time will be increasing with relative to the position of this source, which is moving with the velocity vs. So we can say that we have a v-shaped profile of this supersonic sound waves. Now the wavefront actually extends in 3 dimensions, and the bunching actually forms a cone called the Mach cone. So we have this v-shaped cone which is known as the Mach cone, and that is the situation of the sound wave profile when the source is moving with the velocity greater than the velocity of the sound waves. Now a shock wave exists along the surface of this cone because the bunching of wavefronts causes an abrupt rise and fall of the air pressure as the surface passes through any point. So that is the case, and the shock waves exist for such situation when you have the source moving with greater velocity, and due to that pressure waves you have that shock waves. Or in other words, that pressure wave gives rise to the shock waves. Now from the figure we see that the half angle theta of the cone, known as the Mach cone angle, is given by, if we see this cone represented by this dash line and by this dash line. So this is a cone, and the half angle will be, if we just split this cone which is represented by these dash lines, if we just split this into half, so that this angle theta will be the half angle known as the Mach cone angle. So this angle theta, we have a triangle. See, we have one this side, we have this side, and we have this side. Now this is the radius side, and this one is the distance between two successive or between two wavefronts. So we can say that this is that time, if we could just consider one thing. So if this is S1 and this is S, this S1 is the position of the source when it produces this wavefront, and after time t it traveled a distance vst, so that this side will be vs times t. So in this way we can use this triangle so that defining sine theta will be vt, which is the radius, or we can say this side of this half cone, and we have the vst, which is this side, right, as marked here as well. So by defining sine theta, that will be vt over vst, or we can have this ratio by cancelling out these time factor, so that the ratio of the source to the speed of sound is the Mach number, right? Or we can say that this is 1 over m, or generally the Mach number represented by m, so we can say that this is 1 over m. Now if a plane flies at a Mach number, say 2.3, that is, the speed of that plane is 2.3 times the sound waves. That is, the plane is moving with the speed 2.3, means the speed is 2.3 times the sound speed, the speed of sound in air through which the plane is flying. So in that situation the Mach number will be 2, that is this ratio which is 1 over m will be equal to that 2.3. so that the shock waves generated by a supersonic aircraft is shown here. See, we have the picture is taken from this source, and we have a supersonic jet which produces the shock waves, and that is because the plane is moving with the speed which is greater than the speed of sound waves by an amount 3.3 times. So in that way we can have these pressure waves because of the abrupt change in the pressure. So the shock waves generated by the supersonic aircraft is shown here, produced as a burst of sound called a sonic boom, in which the air pressure first suddenly increases and then suddenly decreases below normal before returning to the normal air pressure. So this is because of the shock waves, and due to the situation when the source is moving with the greater speed than the wave speed. And the wave, I mean the sound waves. Now you need to solve these three problems which are based on the supersonic speed or shock waves given in the module 17.8 following your course book. And with this I thank you for your time, and this was our last lecture of this course. So see you soon next time. Thank you very much.